Welcome back. In this lesson, we're going to look at seafloor spreading. We're going to see that there's various support for the idea that the seafloor is actually spreading and that the ocean is actually sitting on a plate or several plates that are moving around, and that the continents also are moving as a result. So this is all towards the idea of plate tectonics, and most of this was discovered in the 20th century. So let's look at some of the examples. There are actually lots of different evidences that the seafloor is spreading apart from each other. After World War II, there was advances in technology that allowed ships to map the bottom of the ocean. They map it in a lot of different ways. A lot of times they'll use sonar, and then the sound bumps off of the bottom of the ocean and you can detect what's actually there, the features that are on the bottom of the sea. And mountains have been found, and ridges that have been found, very symmetric ridges to where whatever's on one side of this line is also on the other. So you'll detect that not just the features of the topography, but also in this case the magnetometer, which is one of the devices that was developed, can actually detect small changes in magnetic field. So whatever rocks are on the ocean floor, if they were at one time igneous rocks, if they were melted rocks, and anything that would be iron in that rock would have aligned itself while it was fluid, it would have aligned itself with the magnetic field of the Earth. So you can actually detect inside the ground of the ocean what is going on with the magnetic field. Is the magnets lined up? Because essentially any of those iron particles inside those rocks are acting like little magnets. Are they aligned in one direction or another? That gives some indication of what the magnetic field of the Earth was when that rock was melted and then solidified. So the topographic features of the bottom of the sea is extremely varied. There are ridges, there's mountain chains, there's deep gorges, there is trenches. The Marianas Trench is about nearly 7 miles deep, straight down from the bottom of the ocean. Not from the surface of the ocean, but from the bottom of the sea. The trench will extend another 7 miles down. So these are odd features. And another evidence is that if you were to take sediment samples from near these ocean ridges, you're going to see that the sediments are very thick away from the ridges, but very thin towards the ridges. That would suggest that the ridges are actually moving. Also, if you were to take core samples of this, you can actually detect changes in how the minerals are laid down in the rocks, which suggests that they were laid down at different times. The magnetic field of the Earth is very interesting because if you have changes in these rocks that suggest that the magnetic field was laid down when one rock was laid down, then changes to a different rock, gives you an idea that the magnetic field of the Earth has actually reversed polarity several times over the recorded times of the rocks on the bottom of the ocean. So rocks a certain distance from the ridge will have one polarity, and then go farther and it will have changed polarity, and then go farther still and it'll change again. So over the time, it's possible that the iron, the sloshy liquid iron outer core of the Earth, has actually moved in a different direction, which would make the magnetic field go backwards as well. So these magnetic rocks are symmetrical to the ridge. So since it's symmetrical, it's suggesting that the ridge is actually growing rocks and then moving outward on both sides of the rocks. These are named after certain scientists, and they're symmetrical. So from one place, say from the ridge itself, you have certain types of rock with certain types of magnetic polarity suggested, and then its identical twin is on the other side of the same ridge. This is all suggesting that you have a chronology or a time that this has actually happened, so that these rocks are actually being formed and then moving towards the coastlines. Now these ocean crusts would then submerge underneath the continental crusts, which gives much more credence to the idea that that these plates are actually moving around on top of a liquid or semi-solid underlayment. So here's the basic idea of seafloor spreading. If you were to have a crack along the ridge and magma comes up and takes that crack, it will then solidify into rock. And then as the ocean crust moves away towards the continents, you're going to end up with more magma coming in and more rock being formed, and then it's subducting underneath the continents and then melting again. So it is a kind of like a cyclical, almost like a lava lamp, the way that this would work. The oceanic crust being formed at this midpoint and then being subducted under the continents. So the magma is moved towards the surface, and then it fills the crack in between the ridge, and then the oceanic crust moves away from that ridge towards the continents.